In the last video, we talked about how to use Opencv to achieve learn following. As we saw, it mostly relies on hand-tuned parameters to deal with various situations. It's not only extremely time-consuming, but impossible to deal with all kinds of situations. In this video, we will train a deep learning model to achieve learn following. Before moving to model training, let me give you a brief introduction about deep learning. Machine learning is a subset of artificial intelligence, which means computers learning from data using algorithms to perform a task without being explicitly programmed. Deep learning is a subset of machine learning that uses a complex structure of algorithms modeled on the human brain. This enables the processing of unstructured data such as documents, images, and text. Before deep learning became popular, the traditional machine learning methods include regression algorithm models the relationship between variables that is iteratively refined using a measure of error in the predictions made by the model. Instance-based algorithms typically build up a database of example data and compare new data to the database using a similarity measurement in order to find the best match and make a prediction. Decision tree algorithm construct a model of decisions made based on actual values of attributes in the data. It focuses in tree structure until a prediction decision is made for a given record. Clustering algorithms put data into clusters based on various measurements of similarity. Clustering methods are typically organized by the modeling approaches such as centroid-based and hierarchical. All methods are concerned with using the inherent structure in the data to best organize them into groups of maximum commonality. Bayesian algorithms are those that explicitly apply Bayes' theorem about prior and posterior probabilities for problems. Artificial neural network models are inspired by the structure and/or function of biological neural networks. Here I refer to the classic neural networks. Deep learning is also a neural network, but has a different structure. Let's take a little bit deeper look at the curve fitting problem typically seen in regression algorithm to give you an intuitive idea about drawbacks of traditional machine learning algorithms. Curve fitting basically tries to find a function to fit the data to either predict the output for a given input value or separate different groups of data. The more complicated the function, the more capable it is to deal with complex boundaries or curves. A linear function can only represent a straight line. A quadratic function can represent one turn, while a cubic function can represent two turns. This applies to 3D space too, where a surface will be defined to fit the data. As you can imagine, as the input dimensions go up, the function will soon become extremely complicated to solve. For the image cases, even if the image is as small as 100 pixel by 100 pixel, if fitting into the algorithm directly, the input dimension will be 100 times 100 times 3, which is 30,000. To reduce input dimension, people need to extract features from the data first, then feed the features into the algorithm. For example, the edges we extracted from an image in the last video. Also, when data volume goes up, it will become increasingly difficult to make the function fit the data well, because real-life data are not generated by functions, so in a lot of cases don't naturally fit into function definition. These two drawbacks also apply to other traditional machine learning algorithms. This is why they are not very good at dealing with very large volume of data or very high dimensions of inputs. The biggest difference between deep learning and traditional machine learning lies in three aspects. First, the structure of deep learning models are much more complicated than traditional machine learning algorithm. It mimics the neurons in the human brain, where each neuron performs a simple functionality and tons of them together can achieve very complicated tasks. The number of neurons and the connections between them has become more and more complicated in recent years. This diagram shows commonly used deep learning model architectures and how complex they are. The bigger the circle, the more parameters are in the model. As you can see, the number of parameters can easily go up to tens or thousands of millions. The GPT-3 model and MUM model recently released by Google has 175 billion parameters. The complicated structure makes deep learning models extremely powerful in representing complicated data. One thing worth mentioning is that training these huge models was made possible by the increasing computing power in recent decades. Measured by the number of floating operations that can be performed per second, computing power has increased from 124 billion flops in 1993 to 442 trillion in 2020. The second big difference is that deep learning requires much less human intervention. In traditional machine learning, feature extraction is an important part to use domain knowledge to extract features from data to reduce complexity and make patterns more visible for learning algorithm to work. For example, features can be pixel values, shapes, textures, position, and orientation. The performance of most of the traditional machine learning algorithms depends on how accurately the features are identified and extracted. This process is difficult and expensive in terms of time and expertise. On the contrary, deep learning tries to learn high-level features from data in an incremental manner. This eliminates the need for domain expertise and hardcore feature extraction. We will talk a bit more about this later. The third difference is the performance as the scale of data increase. Deep learning is capable of dealing with a much bigger volume of data than traditional machine learning. When the data volume or input dimension is small, deep learning may overfit the training data, meaning it will just memorize all data it has seen, thus fail to apply to data that it hasn't seen before. However, with help from transfer learning, deep learning can still perform well with smaller amounts of data. For images, there are three commonly used deep learning tasks. Classification classifies an image into a set of predefined categories. Detection tells us what objects are in the image and their position. Regression predicts a continuous number from an image. For our learn following case, we need the model to predict the steering angle, so it's a regression problem. Now we have some idea about what deep learning and our task is. The next step is to pick a model architecture. We have seen how big and complex a deep learning model can be. However, bigger and more complex models are not always good. For our case, we are going to deploy the model to Raspberry Pi, which is not very powerful. If we pick a very big model, the inference will take too long to be practical for self-driving. Due to this reason, I picked the model proposed by Nvidia for self-driving cars. Their setup is very similar to PyCar, which uses one center camera to capture images and feeds the images to a convolutional neural network to generate steering angles. This model only has 250,000 parameters, smaller than models in the previous diagram. It has 5 convolutional layers and 3 fully connected layers. The convolutional layers learn filters, which can extract various features that will be useful for the final decision. Here are some examples of filters learned for various patterns of edges and colors. Different convolutional layers will learn features at different levels. It can be low-level features such as edges and colors, or mid-level features such as eye, nose, or high-level features such as faces. The fully connected layers connect every neuron in one layer to every neuron in another layer. It is the same as a traditional multi-layer perception neural network. These layers take the features extracted by convolutional layers as input and do classification or regression. To train the model, we need to collect training data. In the machine learning application area, high-quality training data collection is the most time-consuming, expensive, and important thing to get a good model. For PyCar, we will modify the remote control code and use it to collect data. Remember that the remote control UI has 6 buttons for car movement: forward, backward, left forward, right forward, left backward, and right backward. However, the left and right controls are set to turn at a fixed angle, which is 40 degrees or 135 degrees. This is too coarse to be used as training data. We need more accurate and fine-grained steering angles. So I replaced the original movement buttons with 3 buttons: forward, backward, and stop. The HTML code looks like this. Then I added this as a steering wheel to smoothly control the direction. I use the JQuery roundSlider, which can be customized to different shapes. To use it, we need to add 3 parts in the run.html, the CSS style part, the JavaScript part, and the HTML part. The range of the slider is 0 to 100. We add 40 to it, so the range becomes 40 to 140, with 90 being in the middle, which means go straight. The drag function will be triggered when the handle of the slider is dragged. It will call the fwTurn function to turn the front view. Then I added the Save Data checkbox. It will call setSaveData function when clicked. The setSaveData function will send a request including the updated value for whether to save data or not. This request will be processed in the run function of views.py. It sets a value for saved data and stores it in status list. The status list also has a front view angle, which is set each time front view is requested to turn. Then, in stream.py, we can check the saved data bit. If it's set to 1 and the car is moving, then we store the image and embed the timestamp, current angle, and speed in the file name. For now, we will only use the image and the angle. Now we are ready to collect data. Here is my track setup. I set the speed to 30 when collecting data. This will also be the speed I set when actually doing the automatic lane following. It's easier to control with a lower speed. Driving 1 lap will generate around 700 pictures. It drove several laps, clockwise and counterclockwise, and collected more than 4,000 pictures. It's pretty fast to collect data this way. One thing to note is that when you control the packer to collect training data, you should keep the angle aligned with the track as much as possible. What I mean is that sometimes the track is about to turn right, but the car is at the right edge of the track, so you may want it to move to the left a bit to keep in the middle of the track. When you do this, a left turn angle will be recorded for the right turn track. This will add noise to training data that's confusing the model training. Now we have the training data, we can move to the actual training part. We use Colab to write training code and run training. We can use Raspberry Pi to run the training due to its limited computing power. Colab is a free cloud-based Jupyter notebooks that let you write and train deep learning model in Python. The popular Python libraries supported are TensorFlow, Keras, Opencv, Pandas, etc. The cool thing is that TensorFlow for GPU is already pre-installed. Just remember to choose the runtime with GPU. This will make the training much faster. I have included the link to my notebook in the description. Now I will talk about the key parts in it. I uploaded the training data to my drive directory and mounted the drive in Colab so I can access them. Then I get all image files, store the image file path in image path, and pass angle from file name to store in steering angles. After data is loaded, you can split it into training and validation set. The validation set is the set of the data we set aside to see how the model works on data that it hasn't seen. We usually use an 80-20 split. We can take a look at the angle distribution. If we see some angles are missing data, we can collect more. Here we can see the distribution is as what we expected, with most images around 90 degrees and less data for angles further from a 90 degree. And we can see distribution of the validation data is similar to that of the training data. Then we write the image data generator to read a specified number of images from image files stored in image paths and angles from steering angles and feed them into the training process. The yield here means it will continuously generate the output. Then we define the models. Since this is a regression model, I use the mean squared error as the loss function, which measures the average of squared difference between recorded angle and predicted angle. Then the code for starting the training. I usually let it run 10 epochs, which means iterate all data for 10 times. After each epoch, the model will be evaluated on the validation set, and if it improved compared to the previous epoch, the model will be saved. This roughly takes around 1.5 hours. You can run it multiple times until you don't see improvements on the validation set. Notice the load base here. This tells the model to start from the learning results of the last run and improve from there. After the training is finished, we can check the history of losses. It should drop as training going on. We can also apply the models on the validation set to calculate the losses and take a look at some results. As we can see, the MSE, which is the mean squared error, is 0.88, which means the average difference between recorded angle and the predicted angle is less than 1 degree. This is pretty good. There is one last thing. I converted the model to a TensorFlow-Lite model. A TensorFlow-Lite model is represented in a special, efficient portable format. This provides several advantages over the original TensorFlow model format, such as reduced size and faster inference, that enables the model to execute efficiently on devices with limited compute and memory resources, such as mobile devices or Raspberry Pi. We can see how the TFLite model works on the validation set. The performance of the TFLite model is very close to that of the original model, while the model size is just around 1/3, reduced from 3 MB to 1 MB. On Raspberry Pi, it takes around 0.03 seconds to process one image. We can also compare the results with Opencv. I generated angles with both model and Opencv for images in the validation set, and picked those that one method predicts to go left, which means the angle is less than 90 degrees, and the other one predicts to go right, which means the angle is larger than 90 degrees. For random 100 images, there can be 15 to 25 of these cases. Here are some examples. For the majority of them, the deep learning results are better. Now we have the model. We download it from the drive and store it in the same folder as stream.py. I added one file, learnfollowdl.py, in the same directory to take the image and predict the angle using the model. Here you can see the following code is much shorter than the Opencv version. Now add a button for following in run.html to send the following action. In run function of views.py, we deal with the following action by storing the status in backview status, which will be passed to stream.py through status list. Then in the getFrame function in stream.py, we check the status and call following. Now we finally can get it running. It runs much more smoothly than the Opencv version. And since it's deep learning, if you see it doesn't go well in some situation, you can collect more training data and retrain the model.